Hello again. Happy end of the week. I'm going to continue talking about the transport layer. Now, there'll be a slight overlap at the beginning here. This was where we ended last time. We had a protocol. The computer called it RDT 3.0, I think it was. And the protocol allowed only two messages to be around at a time. They alternated sequence numbers 0 and 1. And I showed some examples of the way these might do things, sending things back and forth. We played around with them some. Now, the next question is, how can we improve these? As I said, that one was terrible. It destroyed the bandwidth. We were wasting our money with how much bandwidth we had to send things. So we got to do things better. Well, one thing we need to do better is we need to put more messages out there at one time. And another thing we can do better is to have both sides be both senders and receivers. That way, it's a full duplex. I can send and I can receive. The new algorithms that we're going to use are called automatic repeat algorithms. And there are two types, the go-back ends and the selective repeats. Okay, so these are the algorithms as they have been in use, and we'll see now what's more or less really there. We might not have as large numbers for the ends I'm going to have, but we're pretty close to what's really done. In the real algorithms, both sides of the connection are senders and receivers. But we don't waste time sending an ACK-NACK alone. We piggyback it on the top of what we are sending. So if I receive a message from the other side, then I wait till I have a message to send, and I put the ACK in a particular spot in the header of my message. So the other side gets the ACK and gets my new message. That way, I'm not wasting time setting up a whole separate message to carry over the ACK and nothing else. Now, that also means I'm going to have to make sure that that I'm not in a very slow period where I have nothing to send. If I have nothing to send, I'll have nothing to piggyback the ACK or NACK on, and so I'll have to send an ACK or NACK alone. I'll have some kind of a timer that will time out if it says you really better send a NACK or you really better send an ACK or a NACK. Don't wait any longer for the application layer to send you anything. And I more or less put these things down here. So to improve the bandwidth, we put more messages out there. We have to choose how many on-ACK messages we are willing to put on the line. Why can't we just go infinitely? Well, that's because we have to save the on-ACK messages in case we have to resend them. And we don't have infinite memory, even today. So we need to make sure that we have some way of keeping track of what messages we've sent already that we haven't received any notification for. We want to make sure that two messages don't get the same message number. That would be a disaster. So we try to prevent that. To do that, we don't use every possible slot we create for sending messages. We leave some of the slots empty. the idea is there's a window. We have a set of possible numbers we could use. Like we could use numbers 0, 1, 2, 3, 4, 5, 6, 7. So we have 8 numbers we could use on the messages we send. We start out by saying we'll use half of them. We'll use 0, 1, 2, and 3. Now, if the user sends us, the application sends us 4 messages, we send them all over. Until we get an ACK, we delay any messages that come from the application layer. We say, try again. We don't have any room. Let's say that the application layer tells us that message 1 has been received. Now we move the window. We say, we have sent 2, 3, and 4. We always want to have 4 we sent 1, 2, and 3. 0, let's say 0 was ACT. Now we have 1, 2, and 3 on ACT. We're going to say, okay, add 1 more. 1, 2, 3, 4. Our new window is still 4 wide. We still have 4 slots, but they start from 1 and end at 4. They're always consecutive, assuming that you're willing to look at it as a circle. 0 follows 7 in this case. So the window is the concept that we have to think about. We choose a power of 2 primarily because we have to put the number in some part of the message. And if we're going to use 2 bits, we only have 4 numbers we can send. If we're going to use 3 bits for the number, we only have 8 numbers possible. If we have 4 bits, we only have 16 numbers possible. So it'd be stupid to use 12 when we have 16 in the 4 bits. So it's always going to be a power of 2. And we're going to have a window of n over 2. So the window is going to be half the size of the top number we can set, the number of numbers the message numbers we can use. The sender has n slots. At any one time, half of these, consecutive half, are holding sent messages, or they're available to send more messages. This method is called a sliding window. In the example I had before, we had the window from 0 to 4. When the 0 was ACT, we moved the window down. We slid it down to 1. Probably at 0 to 3, we slid it down to 1 to 4. If 1 gets ACT, we'll slide it down to 2 to 5. So we keep moving it along. Here's an example. I'm going to look at it as saying, I'm going to show you the message slots, and I'm going to show you the status of each of those slots. There are 3 possibilities. Actually 4. I could have blank. S is a message with this number has been sent, but not ACT. X means that no message has been sent with this number yet. A means this number has a message that has been sent and has been ACT. Why haven't we removed it? Because we have to keep the window a consecutive number of slots. We can't drop one off in the middle. We have to wait until the one at the extreme left, at least, gets pulled off. So let's see what happens here. Let's take an example. Suppose we're in this case. We've sent message 3. We've sent message 4. Message 3 has not been ACT, but message 4 has arrived and we received an ACT for it. the message has arrived out of order. That can happen. So we are waiting for an ACK of 3. The other slots, they're empty. There's nothing in them. We're not worried about them. If the application gives us a message to send, we give it message number 5 and send it. If the application then requests another message to be sent, we give it message number 6 and send it. Now if we get another request immediately, we can't do it. We say, no, you must wait. So the application layer will have to say, okay, I'll wait and I'll try again in a short time. I'll set a timer and decide when I'm going to try again. The slots, I think the easiest way to think of them is that they are buffers that store the messages. So each one of them is a set of bytes that is in the storage that holds the message that we have sent out on that particular setup or line. So while I show that as just having a number in it, it's probably like 4,096 bytes. But it's a slot within here. So there are 2 algorithms that are used. One is called the go back N algorithm. So again, let's suppose we have this setup. Now, here's the point. A timer goes off. In the go back N algorithm, one timer is set for all the messages that are not ACK. We resend all unacked messages when the timer goes off. So in this case, we resend message 3 and message 5, both of them, and we wait. Now we get an ACK of message 5. Go back N says, interpret an ACK to mean every unacked message up to 5 has been received by the other side, including 5, whatever the ACK was. So message 3 and message 5 are now ACKed. Even though we only got one ACK, it covered both of them. So the result is we can get rid of messages 3, 4, and 5. And now we can add slots 7, 0, and 1 as possible message numbers. And the next time we get something from the application layer, we'll put it in 6. And the next one will go in 7, and the next one in 0, and so on. So that is the go back N. The go back N says, go back all the way. Get all of them that haven't been ACKed. The other choice is called selective repeat. Now, one of the drawbacks with go back N is you're resending lots of messages. We could have a window of 16, and we could be resending 5 of them. So, it might get messy to resend so many. It might be costly. So the selective repeat says, this time we're going to put one timer on each message. Now again, that means more cost in this algorithm for the timers. Not necessarily for the bandwidth, but this one will have more timers in it. When the timer goes off, the only message we resend is the one where the timer went off. We don't bother resending it the rest. And when we receive an ACK, it's only for the one that we got the ACT for. It's not for any of the others before it. So if we get an ACT of 6 in this case, it means message 6 was received. We don't know what happened to 3. It still hasn't been ACT. And we didn't send anything, resend anything, because we don't have to. The ACT does not tell us that we have to go back and resend everything that isn't there, is an ACT, or that we have gotten everything before it. So if we got a message of 3 now, 3 was ACT, then we can get rid of 3 and 4, and 5, 6, 7, and 0 is our new sliding window. So this method is pretty good. Well, I mean, it's reasonable. The question is, how much time should we give to everything? We don't want to wait forever to get back an acknowledgement. But on the other hand, we don't want to jump the gun and send it so fast that we don't give the other side a chance to return, to reply. So we got to find out what might be a reasonable number. But that reasonable amount of time would depend on how busy the system is. So it's not one number. It can vary depending on the time of day, or how many people are on the system, whatever. So we have to find a way to make it a dynamic number. That is, it has to be based on what's going on right now. So we can, when we get an ACT or an ACT back, it's pretty easy to compute the round trip time. That's the time from when we sent the message until we got the ACT. If you remember in Wireshark, the RTT is actually computed for us. So it is an important time. Now, if the RTT is the round trip time, we wouldn't want to set the timer lower than that. So that's a good lower bound. But we don't want to cut it too close either. So what we're going to do, and unfortunately they can vary a lot. So the trick is the following. We want to recompute the RTT every time. We start out with some RTT that we have, something to begin with, whatever it is. And we pick a parameter alpha less than 1. Now, this kind of algorithm occurs a lot. We get a new RTT from the next message. We'll call that the latest RTT. What we want to do is recompute the estimated RTT. And we want to have the latest RTT count more than the ones before it. So if alpha is 0.6, that means we're counting the one we had before has 1 point minus 0.6, so it's 0.4 times the old estimated RTT plus 0.6 times the latest. That means the latest counts more than the average of the old ones did. And we just keep doing that. That's our new estimated RTT. Well, you might think, okay, that must be what we set the timer for. Well, not enough. We haven't figured out what to do with the fact they deviate so much. The standard deviation is large. This method is called an exponential weighted average. And again, it's something that comes up a lot. So what are we going to do? How do we compute? How do we give it enough time for the variation? Well, we're going to compute another number, the standard deviation of the RTTs. If you remember standard deviation, you compute the average, then you look at the differences between each case and the average, and square them, take the square root of that and divide by the number of cases, or the number of cases minus 1. Usually it's the number of cases minus 1. Statistically, that's supposed to be better. So you compute the deviation at the beginning. Now, you come up with the latest RTT. I wrote this as latest RTT minus the estimated RTT. I really want to make sure you realize that you're really looking at the absolute value of this. You don't want a negative. You're always computing absolute values. And again, it's a weighted average. Now we're ready, finally, to compute the round trip time. We set the timer. That's 3 times the estimated RTT plus 4 times the standard deviation of the RTT. This is one of those mystical things that comes out of the air. Usually that means, when you see something like this, that this is what experimentation and little mathematical analysis have determined are the best numbers to use. It doesn't say that's written in stone. You might want to try something else and see if it's better. But usually when you see something like this, it means that's what the people think is the right answer. And so that's the way we do it. Now that's as far as I want to get today. The important things for today have been the 2 different algorithms, the new algorithms we have. The selective repeat and the go back in. And also the idea of the sliding window, and that we have essentially full duplex. Both sides are senders, both sides are receivers. And finally, the way we compute the round trip time. You can expect some homework on this. I actually think there's some homework in Ross and Caros that I can use on this. So I hope I will get that out very shortly to you. I hope you've had no trouble getting the book. I presume the Comp Center has set it up. If there are problems, let me know, let the Comp Center know. Again, remember, this book hasn't even been printed yet, the 8th edition. Although I don't know if they got you the 8th or the 7th edition. It doesn't really matter to me. But if you haven't tried to get a hold of the book, please do. Thank you very much. Have a good rest of the weekend.